today I'm here to share with all of you an idea which is basically telling us that we have a very promising candidate in the fundamental physics, which can give us nice insights, very significant insights in order to get the gravitational interactions, in order to perceive more about the gravitational interaction. So that candidate is nothing but the dark matter. So just acting as an outsider, I will ask some kind of spontaneous questions. So what is the dark matter? So observation is suggesting that dark matter should be electrically neutral. It should be stable over the age of the universe. It has to have non-zero mass, and it could be non-baryonic or baryonic. Now, why to study dark matter at all? Because we have strong evidences from the CMB, from the gravitational and astrophysical observations. Like, let us say in the old times, for the galaxy rotations curve, we see the departure in the observed velocity and the velocity predicted theoretically. Now, a more modern technique like gravitational lensing is predicting the galaxy mass, which is again, it's not same as theoretically predicted. And of course, the CMB is there, which is giving us the idea that, of course, dark matter is there through its anisotropies. And it is also telling us very precisely that how much dark matter is left in the present universe. So next, I ask the question, so why to consider the gravitational interaction? So I think it is already answered. All these observations are basically based on the gravitational interactions, and dark matter actually can influence the dynamics of this galaxy. So why the vector boson dark matter? Honestly speaking, I do not have robust motivation for this, other than that it is very much rarely discussed in the literature. Now, let me, from the particle physics point of view, introduce to you a dark sector and a standard model sector, where the dark sector is containing a vector boson dark matter, which is Z2 odd, and also it has a scalar field here, which is actually kept there to provide the mass to the vector boson. It is, let's say it's a non-abelian vector boson. Now, standard model is Z2 even. Now, this is a possible interaction Lagrangian one can design. So rather possible and unique, because in the fourth dimension. So here one can see this VHS has a term, which is lambda HS, where H square and A square can talk to each other. So basically this A square can talk to the standard model sector via the Higgs portal. And don't forget that we will always have the dark matter interacting with the minimal gravity. So now, if we are aiming to constrain our parameters, I mean, to reduce our parameter space. So with this motivation, we remove S from the dark matter sector. And in order to provide the mass to the dark matter, we switch to the Stuckelberg mass mechanism. And here we can see, so the Higgs portal is on, there is nothing called lambda H spring now, but gravity will always be there. So it is pointing towards the minimal coupling presence. So why not to confine it within the minimal coupling and going beyond to the non-minimal coupling? Because you can see obviously that the minimal coupling is always suppressed by the Planck mass. We don't have sufficient parameter which can enhance this much of coupling. So this is a fair motivation to choose non-minimal coupling of gravity and dark matter than the minimal one. So let me now describe our model to you. What we did is that we have introduced the non-minimal coupling of this the abelian vector boson dark matter with the curvature scalar, where this G tilde is basically symmetric, and due to the presence of this minimal coupling with the scalar curvature, this is named as the Jordan frame. So entire action is written in the Jordan frame due to the presence of this non-minimal coupling. The L tilde dark matter is representing the dark matter sector, and this is the standard model sector under the G tilde metric. So now the mathematical steps is very usual. We will use a conformal transformation, put this transformation to the action, and eventually get our favorite action in the Einstein frame, where we can see that now gravity is become canonical. We have a pure gravity sector, we have a pure standard model sector, we have a pure dark matter sector, and a plethora of terms which are interacting with that, the dark sector interacting with the standard model. However, the interaction is controlled by the non-minimal coupling, what we have introduced. So at this stage, I'm emphasizing that G can be taken as a FLW metric for further studies. So So this model here, we are not demanding the conformal symmetry to be retained after the conformal transformation. So that's why xi can be anything, which we will see eventually. It cannot be arbitrarily large. And we have another free parameter mx, which is basically telling us that this model is very much economical in terms of the free parameter. Now, in case of dark matter physics, we have two kind of scenario. One is called the freeze-out scenario. It is all of the mechanism for the dark matter production, and another is called the freezing scenario. In case of freeze-out scenario, if I can refer you to this plot, this x-axis is basically depicting the mass of the dark matter divided by the temperature of the universe, and then this y-axis is basically depicting, let's say it is proportional to the number density of the dark matter. So in case of the freeze out, we have the dark matter particle and the standard model particle. They are in a common thermal bath. They're sharing reaction, interacting with each other. They're maintaining even a chemical equilibrium. equilibrium. But now, eventually, when universe will start to expand, we will see that there will be the dark matter density or the density of the particle in that bath will be diluted, and so the reaction rate will drop. They will not they will not interact with each other as frequent as they earlier did. So now when the universe is expanding, and eventually we will see that the dark matter production will stop, dark matter annihilation to the standard model will stop, and this situation is depicted through this solid colorful line, and this is called the dark matter freeze out. Now in case of so after this dark matter freeze out, we have no dark matter production, we have no dark matter annihilation. It will retain its number density there as a constant, which is basically the present day observation as the relic density. It has to match with the observation. Now, in case of the freezing scenario, it is a bit different than the freeze out, where we can see that initially you can think that the thermal bath is full of standard model particle, but with no or very little amount of dark matter. And this kind of dark matter are very feebly interacting, so that we named them as feebly interacting massive particles. Now, this is a kind of recipe which I'm giving to you, that we need to produce enough dark matter in this duration in order to match the dark matter relic density. So basically tuning the coupling, tuning the thermal bath temperature, which has to be greater than the mass of the dark matter in order to produce it. One can produce the standard model interaction can produce the enough dark matter in the freezing scenario. But after that, when universe expanding and cools down, eventually the standard model particle, it will be diluted. So again, the freezing production will be stopped, and no more dark matter production will be there, and we will get a constant number density, which has to match with the present day relic abundance. So basically, I'm coming to the phenomenology of this model, where we can see at first, let's say the non-minimal dark matter freeze out. Please don't go to the very parameters, all the parameters identification as of now. I can go on after the talk. So this is a very important constraint, that dark matter relic density, which we need to follow. So in case of the dark matter physics, we actually solve a Boson equation, and we find the number density, which will in turn help us to get the dark matter relic density, which now we can see that proportional to the xi square, mx square, which are the parameter of our model. Now in the left panel, the first plot is showing that this blue line is basically satisfying all the relic abundance. Is basically all the points on the blue line satisfying the relic density. This gray region excluded by the perturbative unitarity demands, which predict that the dark matter mass has to be less than 55 TeV. And here we can see that the xi can be approximately order of 10 to the power 30, which satisfies the dark matter relic density. Now, in this case, in our model, we also have a constraints from the direct detection such, where this gray region is excluded, and it is still it is permitting a small amount of this xi of the order of 10 to the power 30 for a lower mass of the dark matter, but upper mass of the larger mass of the dark matter is very much relaxed from this direct detection bound. So this and this two are consistently supporting that xi 10 to the power 30 satisfied dark matter relic density, and the dark matter has to be less than 55 TeV in mass. Now I'm coming to the point of the phenomenology of the dark matter freezing scenario. Again, I'm requesting that please concentrate on this relic density to see that how it is varying and depending on the parameter. Here, the relic density is basically depending on the parameter non-minimal coupling, the reheating temperature after the inflaton decay, and this is the mass of the dark matter. So for a fixed Xi, if I can refer you to this plot, for a fixed Xi, we can see that when the TRH is very small, the mx is small, and as TRH is progressing, the mx is becoming large. All these black lines are basically satisfying the relic density. This green region is a very interesting one. This is basically corresponding to the minimal interaction. When we turned off the non-minimal interaction, that Xi is equals to 0, we will get this region, which is basically Xi not Xi equals to 0. Now here, if I can take you to the bottom plot, here we can have a straight exclusion in this blue line region where TRH is less than mx, so it is not enough temperature to produce the dark matter. So another bound we can have here due to the dark matter thermalization condition, which is basically saying that in case of the freezing, you cannot have the dark matter reaction, the dark matter interaction rate much greater than the Hubble parameter, because then it will strongly couple with the standard model, and it will mimic the freeze out scenario. So this is demanding the bound that Xi has to be less than 10 to the power minus 5. It is predicting a mass range almost kilo electron volt to 10 to the power 10. So now I'm coming to the conclusion of my talk, or the comments. Gravitational interaction is inevitable in case of the dark matter physics, because observation is suggesting so. We have also seen it theoretically. Now, in our work, we have introduced a certain kind of interaction between the abelian Victor boson dark matter with the scalar curvature. We obtained the non-minimal coupling for the freeze-in, for the freeze-out. We have seen that how they are varying. We have also seen that our model, the speciality of our model is that it is a very minimalistic model. It has only two free parameters. Earlier, people, of course, have done this kind of work, but their non-minimally coupled Higgs were also considered, and it acted as a mediator. Now, due to this mediator, the Higgs, the entire cross sections will be so suppressed that we won't get any bound from the direct detection. But our work is liberal to that constraint because we do not have any Higgs mediator. We are getting some kind of contact interaction. So basically, we can have constants from many observations. So Xi freeze-in, as it is very, very less than the Xi freeze-out, it is predicting a cutoff scale, which is almost valid up to the Planck scale. Now, it will be nice to see if more gravitational signals can constrain this higher value of the dark matter mass in this freeze-in production. Xi equals to 0 is telling us that even if you turn off the non-minimal coupling, there will be always a communication between gravity and dark matter. So of course, people have looked for the gravitationally produced dark matter due to the background fluctuation. People are looking for the non-minimal coupling with the dark matter. So recently, I have seen a manuscript where they also included the higher order curvature term like R square in the action. And if you're interested, you can of course see our paper. This is the reference. So the last line is that we are, of course, aware about the quantity of our knowns and unknowns. So this expedition must go on. Thank you.